Esoteric systems are usually a bit more complex, and then we looked into the behavior of the systems. We looked into the uh, pre-post analysis, and we looked into the more towards the qualitative side, which is usually very hard to measure, because you cannot measure a person's pain to after a certain extent. You cannot measure a person's behavior of smoking. You cannot measure a person's concept of school if you go into a rural area. So what do they think of a university? Say for example, in in most of the situation, we usually use antibiotics quite frequently, just like um, like everything. But antibiotics are not prescribed for general illnesses. But if we conduct a survey, in fact, in the not in the rural areas, if we even go to certain areas in Karachi, you would find really funny answers related to that. So you cannot measure the mental um, um, how can I frame it? You cannot measure the mental capacity of a person. You cannot measure the thinking perspectives of a person. So these type of systems are generally esoteric, and the measurements are not possible with physical measuring devices. You don't have a perception meter or something like that to measure a person's perception related to, say, use of antibiotics. So these are we won't be talking about that. So according to the interaction, the systems could be thought of something like that. One thing which is quite people do a lot nowadays, and then this is kind of a pinnacle of doing a good scientific research, is that your research should be applied. Your research should be applicable to a certain domain area, certain area, and we should see the impact of your research. Your research should have the capacity to build capacity among individual. Your research should be scalable. Your research should be able to reproduce itself at different conditions, at different initial conditions of the system. So these type of research is quite into nowadays. And most of HEC's funding, most of international fundings, most of Wellcome Trust fundings are into research, which is more towards the application rather than building conceptual or notional areas of science and knowledge. So esoteric systems are over here. Electrical systems, they are mostly towards design. Electrical and mechanical, thermal and hydraulic systems are towards design and control. Chemical systems mostly deal with control. Biological systems, socio-economic systems, conceptual system, psycho-based systems, and all of these systems are basically, you can see that design is the most concrete physical thing, and speculation is the most towards the notional or philosophical thing. So these are the difference between them. Uh, Now, so these are a couple of examples. This is the example of a mass attached, so spring attached with a damper, and this is B is electrical circuit, and C is a transport system. You can have. I won't look into. I mean, over here. Okay, we talked quite a lot about deterministic systems. We talked a lot about the stochastic systems. Um, in the previous lecture. Some of them are fuzzy systems. We won't go into much detail. So we will just look into the static versus dynamic systems. The system output depends upon the past inputs and system states. However, there are certain systems whose output does not depend upon the past inputs. We called it memory-less systems. Say, so static systems are generally, by definition, memory-less, um, because time is has no significant contribution towards the current state and towards the past state and any connection between them. So these type of processes are called memory-less systems, and these type of processes are called memory-less process. Say, for example, for today's stock exchange rates, the previous day closing index and the trend for a couple of weeks is quite important. So this can't be thought of as a memory-less process. But if a rock is lying on a floor, and then you want to see the equilibrium, and if you want to see the uh, sum of forces acting at any point at that rock, so you don't need to really investigate what was happening to that rock 10 minutes earlier or 15 minutes earlier if you're looking into the current state or of the rock. So these type of systems are memoryless. However, if time has something which is dependent, um, then these type of systems are called dynamic systems. um, Now, so linear versus non-linear system. Remember one thing. Uh, we usually look at the linear systems, or if we are looking at a non-linear system, what we do is we are looking at the non-linear system, a very small fraction of the non-linear system, which in which the non-linear system could be assumed as behaving as linear. So a fraction, so how, no matter the diameter and the radius of a circle, if you take a very very small arc from that circle, if it is significantly small, that arc would look like a straight line. So exact solution of behavior of linear system can usually found by using standard techniques. So we usually look at linear system. All of the control systems theory, all of the control systems theory, look at the systems which are basically linear in nature. So we can approximate the output, we can approximate the major parameters, we can approximate the major predictors quite well if the system is linear. If the system is non-linear, we can't predict anything. So 1 plus 1 is always 2 in linear system, but 1 plus 1 can be anything if we are looking at non-linear system. So analysis of non-linear system is very very difficult. We usually use stochastic techniques for that, or higher level complexities are involved in that. Now, an example of that's why it's written over here. Except a handful of special types, there are no standard methods for analyzing nonlinear systems. So solving nonlinear problems practically involves graphical or experimental approaches. Say look into a very very famous linear problem. This is called Ohm's law. So it's a linear relationship between voltage across a resistor is linear proportional to the current flowing through it. But even for this simple situation, the linear relationship does not hold good for all conditions. For instance, as the current in resistance increase exceedingly, the value of resistance will increase due to increase in temperature of the resistor. So there is one thing we didn't consider in Ohm's law, because in usually in those type of laws and then thermodynamics laws, the patent statement that provided that temperature and pressure are kept constant, provided that temperature and um, resistance are kept constant or something like that. So they work in a certain range. Ohm's law would work really well, but in a certain range, which is called the linear range. Why temperature and pressure is kept constant? Because if temperature exceeds the linear behavior of the system, the system won't be in the linear range then. So the system would transfer into the non-linear range, and the if the system shifts from linear range to non-linear range, the problem is we cannot predict the output. So that's the problem. So total resistance is resistance plus alpha times of t. So what is alpha? The amount of change in resistance is being dependent on the magnitude of the current, and it's no longer correct to say that the voltage across the resistor bears a linear relation to the current. Otherwise RT should be equal to R. So there is alpha time of t. So alpha is the magnitude of the temperature, and T is the temperature, which is actually changing the total resistance. So this could be thought as the non-linear component. If alpha is if temperature is almost negligible, then R of T would become R in this equation, which is quite straightforward to interpret. So if R of so far as R of T is equals to R, Ohm's law would hold, because resistance is also linearly behaving. But if the current uh, is after us, if the current flows at uh, beyond a certain limit, then the value of resistance will increase, and that would increase the temperature. So that will cause us to include that alpha of t, which is called the non-linear part of the resistance. Okay, now coming back to another very famous example, which is called stress is directly proportional to strain. So there is always a restriction in which there is a saturation, there is always a breakdown or material changes with ultimate set, and they can always destroy linearity. So another example could be thought of as If you remember the Hooke's law, so the classical Hooke's law says stress is directly proportional to strain in the linear region. So there are three types of regions. So there is elastic region. So in elastic region, stress is directly proportional to strain. There is another region which is called plastic region, which after that there is a permanent deformity in the material. Say in a spring, there is permanent deformity. So in that case, Hooke's law won't hold. And after that, there was a breaking point. So the material of the spring would break, and there is a so the fundamental background of Hooke's law doesn't exist at that point. So these are special linear systems. Okay, one more thing which we look into the linear system is superposition theorem. Uh, Always remember that if a function, uh, say we call it over here an excitation function e1 of t, so t means it's dependent upon time, and there is a response function omega 1 of t, and they are directly proportional. So somehow the excitation function e1 produce a response function omega 1, and both are dependent upon time. And there is another response function, there is another excitation function e2, which is producing sorry, another excitation function e2, which is producing another response function omega 2. Then the principle of superposition shows that if we sum the left hand side, if we sum the excitation functions, we would get the sum of the response functions. So this happens in linear system. So if there are two type of excitations, we can always transform it into a single part of system. There is one more property of the linear system which is called homogeneity. So what homogeneity says, that if there are n identical excitations applied to the same system, then rather than summing e1, e2, e3, we would only write n times of e1. So the sum would be total number of, say for example, there are three products which are of same price. Say 3,000 rupees for product 1, 3,000 rupees for product 2, and 3,000 rupees for product 3. So what I can do is that I can always write 3 times any product. So that would be the total cost if I need to. So that would be 9,000. So the similar thing happens, that k equal to 1 to n ak ek is equal to n times of e1. So that's actually the total excitation would lead to the total response. So n e1 and then that arrow, so n omega 1. Similarly as over here, e1 plus e2, omega 1 plus omega 2. If there are 100 e1, e2, e3 to e100, and they all are same magnitude, then I can always write 100 e is equals to 100 omega. So 100 is n over here, by the way. So it's similarly, so 100 of e1, because they all are same, it doesn't matter to write e1 or e2 or e. Similarly, all omega would be same. So this is actually the characteristic of the uh, linear system is homogeneity. Let's have a look at it again if you didn't understand that. Okay, there is one more thing I would like to revise, which is differential equation. So this is a linear differential equation. It's a very famous differential equation. It's of second order. So omega is the response function over here, e is the excitation function on the right hand side, and t is actually the time independent variable in this example. Now um, this equation has a very simple solution. You can always look at um, higher order differential equations, or you can always look at linear differential equation. Why it is linear? Because it's always linear in omega. You won't see any second square or cube or -1 or a square root within omega. That's why it is called linear. So it's linear in dependent variable. It's always linear. That's why it's called linear differential equation. So the solution technique, I won't go into much detail into solution techniques. um, in the next lecture we might talk a bit about that, but I'm not personally interested in the solution techniques. um, whether you are very good at solving it by hand, but if you are, that would be an additional advantage. Otherwise I need to you know give a recap, a very quick recap. Okay, now similarly there are two systems, which are the so the other for the first equation, the excitation is E1 and response is omega 1, and for second they are at E2 and omega 2 respectively. So if we add these two equations, we apply the principle of superposition. There are time varying versus time invariant systems. So time varying systems in which are those systems in which time is acts as a significant variable for the dynamics of the system. For time invariant system, no matter the dynamic of the system, time has nothing to do with that. So we would just look into the examples. So it says that time invariant system responses application of input at time instant at and b t minus tau. So there are so if we apply the input over here at time t equal to 0, so the output is something like that. But if we apply input after some time delay, which is time t plus tau, in other words t minus tau, so the same you can see that the profile is exactly the same and output is exactly the same as well. So time has nothing to do. In fact, even if we introduce a delay of tau seconds or tau minutes or tau hours, whatever the tau is, the response of the system is almost exactly the same. So these type of system responses are called time invariant. So it's written over here. So E of t is omega of t, and E of t minus tau is omega of t minus tau, where t is an arbitrary delay. I didn't explicitly said that before, but tau. So if t is t equal to t is over here, and t equal to t minus tau is over here, so you can see that the output, the correlation between the input and output in figure 1, and the correlation between the input and output in figure number 2 is exactly the same, no matter the time delay. So these type of systems are called time invariant system responses. Similarly, if it was time dependent, there was a certain change in the profile of the output. We won't look at the lump things. I'm not interested in it. Okay, one more thing is continuous time input, continuous time output, discrete time input, discrete time output. So these are called continuous time systems and discrete time systems respectively. So analog systems and digital systems. So analog uh, to digital systems. So there we have continuous time inputs, and we can have discrete time inputs, and then there is a discrete system time, and we get discrete time outputs, and there is some converter and analog to digital converter, and then we have continuous time output. So have we can always do processing. If you remember the capacitor, so what capacitor do is we can change type of signals from analog to digital by using a capacitor. So this is a processing of a continuous figure 1.1, different type of signals. This is analog and continuous. This is digital and continuous. This is digital and continuous, and this is analog and sorry, digital and continuous over here. C is analog and discrete, so it is analog, but it is discrete. It is you know we cannot. So in terms of shape profile, a continuous signal is in which you don't need to lift the pencil or pen while drawing the profile. Or for a discrete system, you need to lift the pencil or pen. So that's actually the major distance, the difference. So the four is digital and discrete. I would like everyone to have a look at it. Now, there are a couple of systems I would like to put some pressure on. Some just an introduction. So these type of systems are called hard and soft systems. So hard systems are generally for very well defined problems, but usually problems are not very well defined. There is a certain level of ambiguity in the definition of the problem. So these type of problems are ill defined, no definite solution, qualitative inputs. It's always hard to process qualitative input into an output. Non quantified system, so you are looking at some component which is just recently being invented, and they want you to look at the behavior. So you don't have any benchmark to compare with. So these type of systems are soft systems. So software systems doesn't exclusively follow physical laws. They might have some holes in them. Otherwise, the hard systems may be characterized by the following things. So if you look at it, the problem associated with such systems are well defined. They have a single optimum solution. A scientific approach to problem solving will work well. Technical factors will tend to predominate. So it's more towards quantitative. This is what it's saying. Now the uh, one more thing about the soft system is, if you try to solve it by using in a certain area of the world, so geographic location might create an impact. Say it is sensitive to temperature. So if you work at different parts of the world, you might get different results. But for hard system, you will always get the single optimum solution, and a scientific approach to the problem solving will work very, very well in those cases. Now, the good thing about this book is it has a lot of philosophy involved, and which is actually not very good for you. You can see that the previous concept of repeatability and refutation and reductionism, they basically, I I studied them in methods of proof and philosophical part of the courses I did in my undergraduate. So okay, that's all for chapter number one. I don't think I need to put much stress on chapter number one. Now move to chapter number two. Okay, why modeling? I have answered that. Need for system modeling. There are a couple of things. Models are used to mimic the behavior of system under different operating conditions. This may also be done with the help of experimentation on the system. The systems are usually too expensive. There is a lot of risk involved in experimentation. You cannot look at the abstract specification without doing simulation. Modeling forces us to think clearly before making a physical model. Is there any, uh, there are a couple of modeling design failures which are usually stopped in the simulation process before putting into some factory and then putting into assembly line and then actually producing them. To guide the thought process, this is very important. You do things systematically by modeling to improve system performance, to explore the multiple solutions. Sometimes there is another solution of the problem which is quite simple. Say for example, if you look at the very famous example in Japan, so there was a packaging machine that put soaps into their boxes, and one of the, because it's an assembly line, so we might have faults. So one of the soap package didn't get the soap. So this error was thoroughly investigated, and then what they did is that they installed an infrared camera or something, I don't know, that actually looks into the process 24 into 7. And if there is any problem in the process, it halts the system, and then engineer will then go and investigate what's the problem. So these type of problems are solved like that. But there is a simple solution in Pakistan's factory. The same problem occurred, and what they did is they put a pedestrian fan near the assembly line. So if the box was empty, it doesn't contain soap, that would actually just fly away from the assembly line by the wind pressure. So the wind pressure would guide it away from the assembly line. So that's one more solution. So we can always think of different solution, economical solution by while using modeling. Now, I would really like to emphasize on that figure. There are three types of models. Mathematical models are most accurate, and they have the least amount of complexity associated to them. Then there are artificial neural network models, which are less accurate, but they are more complex. And so as the fuzzy models are the least accurate, and they have the most complexity involved. I would like to include something like that, some line, you know, you can see my cursor, for stochastic models. So they are complex, but their accuracy is usually quite near to or somewhere in between ANN and mathematical models. Now, one more thing is this diagram. So model can be physical and abstract, and then there are certain divisions. So for abstract model, we usually go for fuzzy logic, crisp logic, ANN. For mathematical model, if you see the arrows coming downwards, it's deterministic and stochastic. There are continuous model, S domain, T domain, and usually time domain. You have ordinary differential equation solvers and linear and nonlinear model. We won't go into details of that. I mean, we've looked into certain aspects of this figure, but not all. Okay. Once again, this is a very good table. Uh, so, if English text could be thought as a model, what we write, then its descriptive capability is good. Its ambiguity is very ambiguous. Its manipulation capability is none, and its implementation capability is limited. So, what English text do? It can give us some explanation and some directions. Whereas if you go to the very last, the mathematical models, the descriptive capability is poor. You cannot explain it to everyone. It doesn't self-describe it by itself. Its ambiguity is not ambiguous. Its manipulation capability is excellent because you can always repeat it and then always get the same solution. Otherwise, people can really, um, you know, there are certain cases that there are clear instructions, but people couldn't understand them, or some in some places don't want to understand them. So implementation capability is good. Problem solving and optimization. In between, there are logic charts and logic flow charts and decision table, whose description capability is fair, which are not ambiguous, which cannot be manipulable, but implementation is good, and then they are usually used in computer programming. So these are a couple of types of models we looked at. Now, okay. Complementary pair of variables for different systems. So there are physical systems which are basically mechanical, hydraulic, and electrical. There are conceptual systems which are basically transportation system and economic system. There are esoteric systems which are spiritual system. We won't look at them. So what are the across variables? Xi, which are velocity, linear velocity, angular velocity. In hydraulic system, we look at the pressure, and so these are the x variables, or the independent variable. We looked at voltage, because voltage is always applied and current always flows. So voltage is always on the x-axis and current is always on the y-axis. The traffic density can be thought as x variable, which will be used to determine the output, which is traffic flow rate. Unit price can be thought as the independent variable or x variable, and that can be used to determine the flow rate of goods. And similarly for velocity and force. So these are some examples. This is something I would like you to pay attention. So there are some types of elements which are called A types of elements. So A type elements are dissipator or algebraic components. B type of elements are delay type components. C type of components. C type of elements are accumulator or capacitive type components, or D type of elements are driver or sources, as shown in table 2.2. We'll go to table 2.2 in a minute. Now, so if you remember the electrical system, it is always RLC. So in electrical engineering, we look at RLC circuits. So resistor, inductor, and capacitor. In mechanical system, we look at damper, spring, and mass generally. So dissipator type is resistor that actually dissipates the energy, or that actually we loses some of the energy or some of the input power from those. And delay type are actually spring, inductor, torsional spring, internal delay component in hydraulic. So they actually produces sometimes, say for example, for a spring of a car, if you have the jumps of your car, so if you go if you pass through a really rough terrain, then it would actually damper the effect. So the immediately you get a jerk in your vehicle, or there is some problem or a speed breaker. So that spring actually dampens it. Sorry, the damper actually dampens it, and a spring basically puts a delay to the effect. A very small fraction of time, but it produces a delay. There are something called accumulator, which actually stores the energy. So these are capacitors, mass, inertia, and then liquid tank in this example. If you're looking at hydraulic thing, what are the sources or drivers? Voltage or current are source and driver in electrical circuit. Velocity or force are drivers for mechanical system. For translatory, for rotary motion, angular velocity or torque. For hydraulic system, the pressure or flow rate will actually drive the. So if there is enough pressure or flow rate, there would be some pipe resistance, there would be some delay component which might we might not need output immediately, and there's some be some accumulation of the liquid which is uh, passed at a certain pressure or a certain flow rate in this example. um, okay, 2.7, mathematical modeling of physical systems. They actually have introduced some concepts. So state, if you remember, we talked about state variable in a greater detail in our during our last lecture. So state variables are very important. And if you look at the state equation, so dot means rate of change of x with respect to time, which is dependent upon a times of x plus b times of u. Okay, I think I should talk a bit about exponential uh, behavior of the system. So next lecture I will talk a bit about exponential behavior or exponential logistic curves. Just remind me. Okay, so output z of t is dependent upon x and it's dependent upon u. Now consider an example. So this is the last topic of today. So a very simple example, and how can we formulate a problem out of it? So consider a tank of volume V. Now everyone pay attention, please. Pay attention. I want everyone to pay attention. Consider a tank of volume V. So in this is not just an example. We will try to learn how the problem is being built. It's not just like solving a question and then getting the answer and get 10 out of 10 out for that. Now we would think a bit more towards construction of the problem. Now consider a tank of volume V which is full of a solution of a material A at concentration C. So there are a couple of things. So the material A, it could be water. At a concentration C, it could be any concentration of water. And the tank capacity is V. A solution of the same material at concentration C naught is flowing to the tank at a flow rate F naught, and a solution is flowing out the top of the tank at a flow rate F1 as shown in figure 2.7. We would quickly go to the figure 2.7. So this is the volume of the tank. This is all of the tank. So the input is coming at the rate C naught and F naught towards the tank, and the output is at the rate C1. There are a couple of assumptions. We are assuming a well mixed solution. So the input from C naught and F naught at the concentration C naught and at flow rate F naught is actually immediately get well mixed into the solution, so that F1 contains equal parts of this liquid, and the liquid is same but they have different concentrations, so they are immediately mixed and then they will go to F1. This is very important. We have a well mixed solution. We shouldn't have pockets of mixture. So this area has greater concentration of what is input, the liquid which is coming from here, and this area has lesser concentration. So first thing is important, it's a well mixed solution. If you remember doing experiments in chemistry, you always stir the beaker or something to make it well mixed. The density of the solution is constant, the level is constant in the tank. So there are two more assumptions. The density is constant means it doesn't mean that this is heavier so it would actually sink down. So the density is actually same, and the level is constant. So the level, the tank is of a certain fixed geometrical shape. It's not an irregular shape, so that the level is constant in the tank. Now, what is the data? They have given us some data. So the flow rate for the liquid which is coming into the container or the tank is 0.85 meter cube per minute. So for every minute passed, the flow rate is 0.085 meter cube. The volume is fixed for the tank. It is 2.1 meter cube. So what is C int? So the concentration, initial concentration, and C naught is uh, so C int is actually initial concentration, and C naught is actually the concentration of the liquid which is flowing into the tank at flow rate F naught. So C initial concentration was 0.925 kilogram per meter cube when T was less than equal to 0. When we started our experiment, that was the initial concentration, and the concentration of the incoming liquid, which is coming from the overhead pipe, which is basically 1.85 kilogram per meter cube when T is greater than 0, when the system is, so this is clearly a dynamical system where time has some effect. The system is initially at a steady state, so concentration at any time T was equals to C naught of T, which is equals to C int, or initial concentration. So all three variables are actually same uh, when the system was initially at the steady state, when we start our experiment, when time was equal to 0 or less than equal to 0. But when we started to note the time, then we need to formulate the model. When we started to note the time, or when we switch the stopwatch, when we click the stopwatch, these three variables started to become different. Now, to formulate the model, the following fundamental principles are used. We should have uh, information about conservation laws. We will talk about component terminal equation in a minute. So, what are the conservation laws? Are the laws for conservation for material, energy, momentum, and electrons. So, what is rate of accumulation is rate in minus rate out. So, this is the simplest of the conservation laws we can use. So, what is the rate of accumulation of liquid in the tank? It is the rate which is incoming and rate which is outgoing, and then we just subtract it. So component terminal equation relate quantities of different kinds. So component terminal Hooke's law could be thought as a component differential component terminal equation, and so on and so forth. One more thing is that we assume that they are approximate relation. For a real spring, real resistor, or a real tank, the relation hold well for a certain range only. Outside the range, the relation is non-linear. Say for example, temperature can really cause a havoc on the system. So what are the important variable? Input variable are C naught and F naught, which are actually the from the overhead pipe. State variables are C and F1. F1, so C is concentration and F1 is the flow rate outside the tank. What are the constants? Volume is constant, tank volume is constant. It is assumed over there. So the tank volume is always constant. So tank doesn't change its shape during the experiment. And the last thing is raw, the density is constant. So the density of the liquid is constant, the volume of the tank is constant, and initial value of concentration is C int. So rate of change of mass is flow rate in minus flow rate out. So what is the rate of change? So rate of change of mass. So if you remember, density is equals to mass upon volume. So mass would be equal to density times volume. So this is actually written on the left hand side, and rate of change means d by dt. Now raw flow rate in is the density of the liquid, and the flow rate coming inside. That's why it has a positive sign to it. This has a positive sign to it because it is coming into the tank. And raw F1, so flow rate out, it has negative sign associated to it because the liquid is going outside by that rate. But since we can always start with putting M over here, and then in next step M is replaced by raw into V. Why we did that? Because raw is constant and we can always cancel out raw. So since the density is constant, raw can be taken outside the differential, because the derivative of 5, what would be the derivative of 5x? D by dx of 5x. So we can always take x out 5 outside and then do the derivative. What would be the derivative of 15x cube? We don't need 15 inside to take the derivative. We take 15 outside, and then we take the derivative of x cube only. So the same thing happens here. We take rho outside and then take rho common from here and then cancel it. So rate of change of volume would become zero. Why it would become zero? Because volume is fixed and density is constant. Now, if we put zero on the left hand side, that would become uh, rho f1 minus rho f naught minus rho f1. So f naught equal to f1 is equals to f, because f naught and f1 are equal. So we call them as f. So d by dt of c times of v concentration. So these are the mass equation. These are the concentration equations. So this first equation is for the mass or the volume. Second equation is for the concentration. So d by dt of cv is equal to cf naught plus c1 cf1. If we cancel it, so that would become vd. We take volume outside. Why we took volume outside? Because volume is constant. The same concept. So dc by dt will become, and divide by volume. So this the differential equation. This is a linear differential equation in terms of c, and actually we need to find the integrating factor for that. But I don't want any one of you to find integrating factor right now. This is the course for first order linear ODE, ordinary differential equations. So have a look at it. Anyways, the solution is over here. I am particularly interested in the solution, so that's why I'm zooming my screen. So this is the solution. What does it mean? Is there anyone in the class which can just translate the solution to me? Hmm. What this equation is saying? Okay, as expected. So the concentration in the tank of the liquid in tank at any time t is equals to the fixed initial concentration, which is the linear part, plus k times exponential decay part, and decay is happening with respect to time. So concentration at any time t of liquid in the tank is equals to initial concentration plus k, any constant, doesn't matter, exponential minus f upon v. So f is rate of flow, v is volume, and divided by t. So this is actually what's happening in the system. So anytime, at any point in time, we can always find the concentration after 1 minute, after 2 minutes, after 3 minutes. What you have to do is to replace t by 2, 3, 4, and get the value of fv and c naught. You will get the answer nk. Now, so initially at t equal to 0, what happened is that if t equals to 0, this would become 1, and that would become c naught plus k. So initial concentration is ci minus c naught. So they replaced k by c initial minus c naught fixed, and that's all. So how can we solve it by using MATLAB? Now this is the same example, and this is the figure. If you look at the x-axis is the time, and so this is the solution. So independent variable over here is time, and dependent variable is concentration. So on x-axis it is time, and on y-axis it is concentration. So as the time passes, the concentration initially, because of the water coming uh, from the top, the concentration starts to increase until and unless it will reach to a steady state. So after that, no matter how much the liquid you add, the concentration will always remain same. That's why it's going toward the steady state. This is the dynamic response. What we can do is that we can always give it a try in MATLAB. And if I run it till here, so what was the syntax error by the way? Oh, so is there anything else? Okay. Always remember whenever you copy and paste, make sure that there are certain things in MATLAB. It's actually the interpreter problem, text interpretation. So you need to give it a go, give it a good look before just copy paste and running it. Okay, please run. So actually, what's happening over here is run till here till line number 9. Mm, just give me a second. It might not be visible to all of you. Fonts, that's too much. Okay, till line number 9, we are just initializing and nothing else. We need to solve the differential equation. So we so we have just, if you remember in the numerical methods, we usually take x equals to a fixed number, and the more the accuracy, the more the distribution of x, the better the accuracy of the system. So I run it by to 1000 time, and then x1 is actually will accumulate the solution for every value of n. So till n equal to 1 till 1000, and then the step is 0.01. So it will run 1000 times. If I put a breakpoint just like I did over here, and if I step it, so at the first place you can see x1 is 0.0925 and 0. So that should be the initial concentration. So look, C is 0.0925 and time is 0. Look, C, x1 contains C and then T. So when I run it at the first time, it should always have the initial concentration and initial time. We start at t equal to 0. And then if we go, so this is actually the differential equation. dc is equals to f c naught c minus c divided by v. If you look at over there, uh, so here 2.9. So the differential equation representation is over here, and C is equals to C plus dt multiplied by dc. So dt multiplied by dc will give a solution, and total concentration would be C initial concentration plus the concentration we apply after the rate of change. So total concentration C is equals to initial concentration, old concentration, plus change in time times change in concentration at any time. So if I step it down, I can see the new value of C. So DC is being calculated. So the change in concentration is 0.034. And if you see, initial concentration was 0.925. So what they do is that they would multiply DC by dt, which is 0.01. Dt is over here. Where is dt by the way? Okay, dt is over here. They would multiply. So that would be 0.01 multiplied by what is DC? 0.0374. So actually this would be added to the concentration. Or if I write C plus answer, so that should be, it won't make much difference. So it's 254, it was 0. So this is just being added. So if I take one step, you can see that the same answer, the C is changed now. The same as I obtained at the answer. Initially, what was the value of C? It's 0.925. Now it is 0.9254 because of adding dc multiplied by dt. And then the next time step would be t plus dt. So initially time was d0. The next time step should be 0.01, and then you can see that it's zero point zero 0.01. Since you might find it a bit problematic to understand at the first place, let us do it again, because it's 10,000 steps. So at next time point, it says that store the value of C and T. What is the new value of C? Plus 9254. What is the new value of T? 0.01. What was old values? 0.925 and 0. When I just do one step, look what happens. That stores the new value of concentration, and x1 stores the new value of concentration, x1 stores the new value of time. And then the similar thing happens. We calculate the rate of change of concentration. Now we have the rate of change of concentration. Now new concentration would be dt multiplied by dc. You can always multiply 0.01 multiply by 0.0374 and then add it to c to get the new concentration. What is new concentration? 0.9257. What is new time? It should be zero point zero 0.02. Look. And then if I continue it again, my new x1 values are over here. So let's repeat it um, 1000 time and then see what happens. 10,000, sorry. So the concentration will go up initially, and you can see that the time axis is 9, 9.01, 9.02, 9.03, 9.04, 9.05, and so on and so forth till 10. So we run it till 99.99. So we run it till 100 steps, and then see the answer. What would happen to the answer? So if time step was even smaller, we just have only run it till 10. So if I run it right now, because the time step is even more smaller, then the total time would become 10. So if you look at x, so it's 9.999. If the time step becomes larger, we can run it till 1000. So it's over there. And if I look at x1, the behavior of the system is actually more towards 1000. And if I look at it, you can see that the equilibrium behavior is more evident in if the time step is increased. Or, the most of the changes actually between 80 and 90, the it starts to getting flat between say 80 and 110. So if I only run it till 100, this is actually now what would happen. I will get the point in which it's not necessary that I can only run it till 100. I can change in this to run it till 200 and more towards. I can change this again to run it till 50 only. I just wanted to look at 50. So you can see that time is 50 now, final time. And if you look at x1, it will only run until time becomes 50. So this is the behavior of the system. So the dynamical system has different behavior at different time points. And if you look at, if you change the time step, I won't recommend changing the time step. If you change the number of times, the number of points you want to actually integrate this differential equation, you can always have different solution from that. So I think that's enough for today.